Welcome back. I'm talking to Andrew Johnson about the creation of the Earth and a new theory which suggests that the Earth has expanded from a much smaller sphere but has not gained any mass. Now, this is Peter Woodhead's idea, and
yes.
You met Peter Woodhead, what, about a year ago, something like that? Or
yeah, it's a bit longer than that, but yeah,
so
essentially.
just tell us what conversations you've had with him in developing his theory.
Well, this was the thing. I'd agreed with Neil Adams and Peter and James Maxwell that the Earth must have been a different size in the past. It must have increased in circumference, in radius, and so forth. And Peter wrote to me. I think he'd seen me on Rich Planet actually, and we talked about Keith Hunter, and Peter had watched that program, and that set him thinking. And then he says, "Oh, Andrew, I've got the explanation for how the Earth has expanded." And I thought, "Oh, that sounds interesting." And eventually I was able to meet up with Peter, and he sent me some of the calculations he'd been doing, because he has made some calculations, which we may talk a little bit about, although they're not essential to describing this theory. And it is a theory, but I think there is sufficient evidence to back it up that I think it is probably correct. He'd seen some research about looking out into the distant sort of distant parts of our galaxy, or the stars in our galaxy, and astronomers in Atacama, they call them the Atacama astronomers, a team in Atacama, they'd observed what they called a snow line around a star. So they had a star in the centre of this solar system, and around this they'd observed a sort of ring of frozen water. And I think this idea was mentioned in this article about this snow line around this star, that the planets were forming there. So Peter thought, well, hang on a minute then. Maybe that means that when the Earth formed, it wasn't all this hot bubbling, mass, from that was spat out of the sun or whatever, or spun off from the sun, or accreted from various rocks that were floating around, crashing into each other. Actually, what was there was primarily ice, and it was formed from a lot of ice. And then around the ice, you had the rocky layers, the heavier elements, the metallic elements, and so forth. Obviously, everything we've got now. And so that formed into a globe, and it was a smaller globe than it is now. And but essentially, it wasn't this primordial fireball. It wasn't like that. It was much cooler than that, and maybe not. A lot of it wasn't that much hotter than room temperature. And what Peter has argued was that actually the core of this ball of the Earth was actually ice, and it actually was, physically a solid block of ice. And so you had the ice in the core of the Earth. So we started off with an ice core, and then around that you had this rock and these heavier elements, including radioactive elements, for example. Everyone knows that radioactive elements are a source of heat. And so you get in that radioactive heating, and Peter's cited some articles which show that a large percentage of the heat in the Earth's crust comes from radioactive isotopes. So there was that. So what you've got is radioactive isotopes around the ice core, gradually heating up the core. And there's a limited place this heat can go. It goes into the core. And what James Maxwell observed is that for up until about 300 million years ago, there was no Earth expansion. That from the geology that he'd done and looked at, James Maxwell said there was no Earth expansion until about 300 million years ago. And then all of a sudden, boom, it starts expanding. And it expands exponentially as well. So what Peter argues in his article is that the ice core, over billions of years, in fact, 3,700,000,000 years approximately, the ice core had gradually melted, turned to water, and then the heating continued, and then 300 million years ago, the water in the core started to boil. So that boiling water then started to create pressure, and then that began to make the outer layers expand, and that's why the expansion only started about 300 million years ago, and it's still going on today.
Now, this is all spinning as well.
Yes.
And you cite a NASA experiment which has clearly been done in zero gravity of a sphere of water, a solid chunk of water in a sphere as it would
We'll
be
show this video,
in,
yes.
in zero gravity, which is spinning.
Correct.
Which is water in zero gravity spinning.
Correct.
Which is similar to what he's saying that the Earth started
Yes.
as.
Yes.
But they inject some solid material into that as it's spinning.
Yes.
And just explain what's going on, Andrew, in this clip.
Well, if you look at that clip, it's I think they explain it in the clip itself. You'll see that the heavy materials actually go to the outside. And if you take this droplet of water, maybe it's just like a teaspoonful of water, and you can add to it because you're in zero gravity. You can make this sort of globule of water bigger, and it does form a perfect sphere. You inject air bubbles into it, and the air bubbles don't come out and fly out. They actually go to the centre. So the lighter materials end up in the centre of this droplet of water. Mm-hmm. So we're saying that what actually happened with the Earth was when the water started to boil and become water vapour, although we got pressure, some of those gas bubbles actually ended up in the centre of the Earth, because what we argue is that the way that gravity works inside the Earth is different to what the textbooks say. Right.
Now let's come on to that then. So the two researchers that we mentioned earlier, James Maxwell and Neil Adams, are saying, well, if the Earth is growing in its circumference, there must be some more material being put in.
Correct.
Whereas Peter's saying, no.
Correct.
It's changing its topology, if you like, i.e. there's something in the centre which is pushing the mass out like this.
So the mass distribution changes, correct.
Right. Now, wouldn't you think then that the gravity would be constant when the dinosaurs are around relative to now? How does that expansion of the same piece of mass give you an increase in the amount of gravity? Because that's what we're saying, isn't
Correct,
it?
correct.
Right.
And then this is where we get on to some of what you'll find on the various physics sites, which Peter and I have looked at. Now, Peter does a bit of maths. We've got some calculations in the paper. We've calculated the volumes of the spheres that are involved in this, and we've calculated some of the masses and things like this. But we haven't, for example, the physicists will argue that this idea is just nonsense, because all the Earth's mass acts as if it's concentrated in the centre. End of this idea that gravity is different in the centre of the Earth or whatever, and you could have gases there. They say that's totally ridiculous, because the gravitational force of the outer layers prevents that from happening. And then we get onto this thing called the shell theorem, which is Newton's shell theorem, which argues and they would say proves that this idea of what we are suggesting must be wrong, because when you do the calculus, when you do the integration of all the sum of the effects of these little slices or rings of mass, it comes out that they negate each other, and you end up with what is the accepted form of the force of gravity. In other words, when you do a force of gravity calculation on a satellite or somebody at the surface, you use the radius of the Earth as the r in the f gm1 m2 over d squared. You use the radius of the Earth. What we're arguing is that that's not the correct way to do the calculation. We argue that because more of the mass is higher up in the crust, and the centre is essentially gas filled, where you haven't got a lot of mass, you've just got the gas, you then get this. If you calculate the force of gravity acting not from the centre but from further out in the shell, that's when you get a lower figure in the divisor at the bottom, so you end up with a greater force.
Right. All right. Well, my understanding would be that if you're considering celestial bodies as masses, because they're so far apart, you can consider them as points of mass with that Newton's equation. But as you get to the surface of the Earth, really, if you've got an object on the Earth, the mass of that object is being attracted to every single piece of mass within the Earth. So you would need to have an infinite number of equations, i.e. an integration from that mass to every point on the Earth, and you'd need to do calculus to do that, right, to work out the force of attraction of a sphere on another sphere. I wouldn't know how to do the maths of how to work out the force of attraction of an eggshell type object to another object, or whether, if the mass is distributed all as one ball, would the gravitational pull be less than if it was a large shell.
Right.
Now,
I
wouldn't know.
I don't know how to do that either.
It's probably some quite complex calculus.
I think it is. Yes, it is. It's some complex calculus, and I'm sure there's maybe a viewer that can do that and help us with that.
But you have Peter and Andrew have authored 2 papers on this, and you have done some calculations on that.
Yes.
Yeah.
We've done it. We've done like Peter's have done like an approximate integration method just by using a spreadsheet. So we have tried to do it in a slightly different way to illustrate, what we're making the argument for. But what we, putting the calculations aside for a minute, it's well known that we do have gravitational anomalies, and they've been measured. I mean, we've cited a couple of papers. There's a paper about the different, or an article rather, about the different forces of gravity. The greatest force of gravity measured on the Earth. They did a survey 2 or 3 years ago, and they found that where the strongest force of gravity is and the weakest force of gravity is, and the weakest that they've managed to measure is 7,000 meters up a hill, I think, in Peru. And so it is well known that we have these gravitational anomalies. Now, as we were discussing earlier, Richard, my understanding, if anyone wants to correct me, that's fine, but my understanding is that that's how they prospect for oil. They look for gravitational anomalies because the different rock formations have different forces of gravity, and they can measure sort of microgravity, and that's how one of the ways in which they find oil fields. Yeah,
tiny changes in the gravity.
Right.
Would you not get that with a solid Earth?
Well, you would, but we would argue it's more pronounced,
right,
because you've got this gas-filled centre. Mm-hmm. And of course, one of the things that I haven't said with this gas-filled idea is that we've got this transition layer where we've got the gas in the centre, and we've got this what we call the boiling layer. So outside of the gas, you've still got this layer of water which is boiling away. And so what we would argue is that if we had this core of ice in the Earth's centre, and it was there from day one, basically, when it coalesced, that's where the oceans came from. In other words, when we get a crack in the crust that's sufficiently big, for example, caused by a cometary impact or some catastrophic failure of a crustal region, out comes the oceans gushing into and forms the deep oceans.
Yeah, and it also explains why the continents seem to fit together.
Exactly, and that is what that's why Maxlow and Neil Adams' research, they illustrate that so well, that the continents, we didn't state the obvious on this yet, but if you look at the globe, everyone's seen, as I said earlier, that the coast of Africa fits to the coast of South America. But when you do what Neil Adams has done, the continents also fit on the Pacific side as well, not just on the Atlantic side. If you go the other way, they all fit together.
So it's hard to believe that they were just moving about. It's
right.
Suggesting that they were once like that and they've gone like that.
Right, and I mean, I've got an animation which I show in one of the presentations, which is the standard, what they call the Pangea model. But they say that these continents were kind of randomly floating around, crashing into one another. And if you look at their animations from some of the university website, they do actually start to look a bit ridiculous, really.
Right. All right. More on this after the break.